right, great. So hello everyone, I'm Jaro Hokkanen from Forschungszentrum Jülich, and I will discuss the performance portability on HPC accelerator architectures and describe the approach chosen in ParFlow along with the newest developments. And at the end, I will show some results run across hundreds of nodes of the JUWELS Booster, which is the top 1 European HPC system on the November 2020 top 500 list. So what is ParFlow? It's a 3D hydrologic model that simulates variably saturated groundwater and surface water flow. It can be coupled with land surface and climate models using the OSIS coupler library, and there is also support for the data assimilation framework, PDAF. ParFlow has a long development history that started at Lawrence Livermore National Laboratory in the 90s, and there exist more than 90 publications describing its application to diverse systems around the world. And ParFlow numerical model is based on finite difference and finite volume schemes, and it uses implicit time integration. The computationally expensive nonlinear problems are solved using Newton-Krylov methods, and more specifically, there is a GMRS method with multigrid preconditioning. There is also a large number of numerical kernels, and none of these actually dominate the runtime. And the database itself consists of approximately, the code base consists of roughly 150,000 lines of C and is available on public GitHub. So what do we need to consider when adding support for accelerator architectures? There are many constraints that are important, and some actually contradict others to some extent. And the first driver to support accelerators is, of course, better performance, but implementation aspects are very important as well. And we would ideally have a single source application that is maintainable in the long term with minimum reliance on external dependencies. And the accelerator utilization should be separated from the numerical implementation, such that the so-called scientific developers should not need to care about all the low-level architectural complexities. And also adding support for new different architectures should be as easy as possible. And our solution for this is to add this support for accelerator devices into ParFlow embedded domain-specific language, or ParFlow EDCL, as we call it, which is a macro-based abstraction layer hiding the architectural complexities. All right, so this is how the interface of this ParFlow embedded domain-specific language looks like. It's used for different types. For example, we can allocate storage for them. Some of those are like vectors or matrices. We use it for message passing for these same data types and accessing certain data or launching compute kernels. And here now in our case, it of course helped a lot that we had this implementation in place. But even for projects for which that is not the case, adding a minimal abstraction layer into the code base for memory management and compute kernels would be enough to benefit from such approach. And in ParFlow, these are accessed using C preprocessor macros, such that different architectures, or more precisely, actually accelerator programming models, use the same interface but separate macro definitions, so that we choose which macros we want to use at compile time, depending on the desired architecture for which we compile. However, in a general case, this approach that we use, it doesn't need to be even based on macros. For example, with pure C++ projects, function objects or lambda functions could be used directly. And the first backend implementation for GPUs in ParFlow was based on CUDA C++, but using a general enough third-party library such as Alpaca, Cocos, or Racha, for example, to target more architectures at once would also be possible and easy to implement. And we actually recently just added Cocos into ParFlow to demonstrate this and make ParFlow ready for the upcoming AMD GPU architectures. And the implementation, we have leveraged some of the most recent technology for best performance and productivity, such as the following. So the first one is unified memory, which is very convenient and improves the developer productivity and code base maintainability quite a lot, because we can use the same pointer to access either CPU or GPU memory. The second thing is host device lambdas, and these allow passing lambda functions to GPU kernels, and I will get back to this with an example. And the third is pool allocator for unified memory, which improves the performance quite a lot in ParFlow case. And finally, we can also use CUDA ever MPI library, which allows us to use efficient GPU-GPU communication with application-side GPU-based data packing routines. All right, and in ParFlow, the memory is allocated and freed using this EDSL API. And this is very nice because now it's enough to modify these EDSL header files to make the data available for GPUs using unified memory. And the same is true for compute kernels, which also require a new header definition for the looping macros, but we can still use the existing loop interface. And all this is done compilation unit by compilation unit, which allows incremental development and flexibility, and also results in slightly better performance because we can only use unified memory and GPUs for compute kernels where this actually beneficial. So in other words, this means that loops in some source files may run on the CPU and in others on the GPUs, even if they use the same looping macro. And here on the left-hand side, you see a typical example of a loop over the grid cells from ParFlow. And by loop body, I refer to the contents within the curly brackets. And this loop body is passed as an argument for the preprocessor loop macro. And this argument, it can be hundreds of lines of code, for example. And on the right-hand side, there is a specialized GPU kernel call example. However, the problem with this example is that if we have 100 different box loop I0s with different loop bodies, then we would need to write a CUDA kernel for all of them, and that basically messes up all our source files. So this is not a very productive idea. And it's also not good in terms of the code base maintainability. So what is instead done is exactly the same as what was done with the memory management. And we just write another box loop I0 macro and use that when compiling the GPU version, so that all loops found from a particular compilation unit run on the GPU without ideally modifying the loop interfaces in the source files at all. All right, so here is how the loop macro definitions look like. On the left-hand side, there you can see the simplest loop macro over the grid cells found from ParFlow that actually runs sequentially on the CPU. And on the right side is the corresponding GPU macro, which uses CUDA. And here the loop body represents all the lines of code that were placed inside the curly brackets when calling these macros in the previous slides. So on the left-hand side, this loop body is just placed inside the loops, which is quite simple. And now for the GPU version on the right, this same loop body is instead used to form a host device lambda function. And all variables that are found inside this loop body are captured automatically by this lambda function by their value. And now we can just pass this lambda function, which has all the required information about the loop contents for the GPU kernel, which then does not need anything else than just call this lambda function. So essentially, the lambda function contains all the arguments already, so we don't need to pass any of that information, which is loop dependent for the GPU kernel. And here, this slide is now showing the differences between the macro based on CUDA and the macro based on CoCos. And the CUDA macro on the left-hand side is actually the same macro that was shown on the previous slide already. So actually both these backend options here work very similarly by using this lambda function approach. Basically, the CoCos library requires first defining an execution policy and then calling the parallel for function, whereas CUDA only requires this GPU kernel call. And then this is how the GPU kernel for CUDA looks like. So apart from determining the correct loop indices, ij and k, the only thing is to call the lambda function. And when using CoCos, writing GPU kernels is of course not required because they are defined in the CoCos library itself. But this is pretty much how the loops work. And there are some other loop types as well that may be required, such as parallel reductions, but these can be done using exactly the same principle. All right, and here is a simple complete hello world example on how the approach can be used. So let's look at the driver function on the right hand side. So this one here. So when we want to run the application, we first allocate, we want to allocate this unified memory and this array of integers of size nx. So we have this alloc manage macro call here, and the macro is defined in a header file here. It's this alloc manage. It actually wraps this static inline function inside. So basically what it does, it calls CUDA malloc managed here. And this, therefore, it allocates us unified memory. And then we have this loop here, which for which we use this box loop macro, and the loop body is here within the given within the curly brackets. Right now it's just one line of code, but it could be more. And this box loop is actually defined here. Well, this is the switch. So basically now it's calling box loop GPU. We could just uncomment this and comment this. So then we would call the CPU macro. Basically, this stuff would be done by the CMake automatically during the configuration process. But for simplicity, it's just done this way in this simple example. But anyway, the box loop calls this box loop GPU macro, which is defined here. So as I already shown some examples of these macros. So basically the loop body creates a lambda function here. So this loop body is just the same as this line of code here. And then that line of code is passed to the GPU kernel right here. And the GPU kernel is defined here. And it doesn't really need to do anything else but determine the thread index, which is just this is just a one-dimensional problem. So there is just one index, and call the lambda function. So basically, this lambda function here is just this one line of code here. And then after we run this initialization loop, we run another loop using the same macro, but now the loop does something completely different. So now it just takes our initialization from the array and prints this hello from GPU thread. And basically the same lambda can here perform different logic, but we still use the same loop interface. And then in the end, we free this managed memory using this free managed macro, which here ends up calling CUDA free. And yeah, that's pretty much how it works. And here we have some results. The plot on the left-hand side is a comparison of running ParFlow with and without GPU acceleration on a single JUWELS Booster supercomputer node at Forschungszentrum Jülich, Germany. And when running without GPU acceleration, all 48 CPU cores are used. Whereas with GPU acceleration, we only use 4 CPU cores and 4 A100 GPUs. The left vertical axis is a performance metric represented by lines, and the horizontal axis is the problem size. The red line is the CPU only result. The purple line is the GPU result using COCOS, but without unified memory pool allocator. The blue line is COCOS with unified memory pool allocator, and the green line is the CUDA result with unified memory pool allocator. And from these, we can make 2 important observations, which are that the pool allocator is extremely important for ParFlow because there are recurring memory allocations and deallocations in some loops in ParFlow. And also the other observation is that using CUDA directly leads to better performance because not all CUDA features are actually available in COCOS. And the right vertical axis is the relative performance multiple between the green and red lines represented by sallow circles. And we are getting almost 30 times speed up for the biggest problem sizes that fit the 40 gigabyte GPU memory when we use this CUDA backend. And the right plot represents weak scaling between 1 and 256 nodes. The vertical axes are still the same, whereas now the horizontal axis represents the number of nodes. And the relative performance flattens out after 16 nodes at 26 times speed up with CUDA backend, which suggests very good scaling across a large number of nodes. And furthermore, the performance difference between CUDA and COCOS backends appear to remain roughly constant during this weak scaling experiment. All right, and to summarize, the ParFlow results from the JUWELS Booster supercomputer demonstrate very good weak scaling across hundreds of nodes with up to 26 times speed up from GPUs. And the GPU support is hidden into a macro-based embedded domain-specific language, which resulted in good developer productivity and code base long-term maintainability along with a good performance gain. An existing DSL is not required for benefiting from our approach, but only a minimal abstraction layer for accessing loops and memory operations is required. Unified memory can play a very important role in good developer productivity, and a pool allocator for GPU memory can improve the whole program performance very significantly, as was the case with the ParFlow. But this is, of course, very program dependent. And something that also comes up frequently is whether the approach can be applied to Fortran projects. And the answer is yes. A colleague of ours has actually applied this approach successfully to an atmospheric model, which is written in Fortran using CUF kernels instead of Lambda functions. And finally, the background here is actually a ParFlow result from a global surface drainage simulation where thanks to GPUs, we were able to run it on a global scale. And yes, that's pretty much everything. Thank you for your interest.
Thank you very much, Jaro. Does anyone have a question?
Bruno, nothing from me. I have a question regarding the memory model, which is not totally clear. I mean, it's not. So the variables that you have in ParFlow, they exist like in both versions on the CPU memory and in GPU memory, or you have part of them that just exist in GPU memory. What I'm thinking of, so you understand my question, is that is point like IOs or checkpointing or these kind of things where you need to grab at some point, make a copy of the internal state of the applications. And so you need to access variables. So we basically, the people could like ParFlow being equipped for doing checkpointing, and we know where it is in the CPU memory. But then when you introduce the GPU, do we need to update this code, or we don't have anything to change just because the GPU just duplicate the data into the data is just duplicated in the GPU for acceleration, but we still keep the same, let's say, memory image on the CPU level.
Yeah, so basically this is handled by the unified memory approach. So those variables that need to be modified or read by the GPU are allocated using unified memory. So then anytime there is, let's say, IO operation and CPU needs to access some data that has been previously modified by the GPU, there is this automatic unified memory mechanism where CPU trying to access the data triggers a page fault, and then this page fault triggers a memory transfer from the GPU to the CPU, and then after that operation is successfully finalized, then the CPU just continues with the IO operations. And then the same happens again when the GPU needs to access some data that has been potentially modified by the CPU. It just triggers a page fault, and then that triggers memory transaction from the CPU memory to the GPU memory, and then GPU continues calculations. So basically this happens background by the CUDA, and it's not shown in the source code. There are no explicit memory transfer calls. It's just everything is automatic thanks to unified memory.
Okay, thank you.
Anything else?
I think Georg has a question.
So thanks a lot for your interesting talk. So I am wondering if this automatic page migration or page replication feature is also responsible for the obvious high overhead at small domain problems or small problem sizes, because obviously you don't have enough memory in the GPUs that your performance saturates at the end. So can you comment on that?
Yeah, so I think, yeah, GPU memory is one bottleneck here, that we could get a little bit better performance with the GPUs with more memory. I think there are now those A100 cards with 80 gigabytes of memory as well. But let me go back to the previous slide here. Yeah, so we could, those curves are kind of flattening. So I wouldn't expect massive improvements anymore. And there is also other aspect on this, that if we want to increase the per node or per GPU problem size even further, then the practical like simulation speed could become quite slow. So if we, let's say, want to simulate I don't know how many days of real time, then that could actually become too slow, and then the practical simulation size could still be less than the actual maximum relative performance peak that we can see from the plot here. So I guess those are like practical considerations versus the theoretical maximum speed up. So they are kind of, there's a difference.
But then the obvious question arises. So did you try to identify why you have this large overhead, this long increase in the performance? So what would be the measures to boost the performance at smaller problem sizes?
Well, that's kind of, that's just the hardware limitation, because with smaller problem sizes, we don't really fill the GPU resources completely. So they are not kind of, we are not leveraging them 100%. So that's just the problem. We can get the most benefit from using GPUs for big examples, but not really small examples. So if you want to run a very small problem with a small number of elements faster, then GPUs are not very much of help for us. It's more like if we want to increase the number of elements, then using the GPUs becomes more helpful.
So would a stronger CPU help you?
That's also interesting question. For example, now when we use GPUs, we are not even using the we are not even using the CPU resources fully. We only use the same number of CPU cores as we have GPUs available, because almost all the calculations are offloaded to the GPUs. And the reason for that is that if we wanted to simultaneously leverage all the available CPU resources as well as the GPU resources, that would complicate the implementation itself very much. And that's also negative and problematic in terms of code-based maintainability and things like that. And then also the benefit of fully leveraging the CPU as well is not that massive that we necessarily want to sacrifice with the code-based maintainability among the other things. So I guess it depends in which way the CPU would be better. Would it be just more threads, or would it have faster clock speeds? But I don't think the CPU would in fact provide very significant performance improvements here. So in our like the way we run these simulations, if we got to choose what kind of hardware we have, we would just take quite cheap CPUs and then put all the extra money into better GPUs, and that would actually benefit us in terms of performance.
Oh, yeah, thank you for this very interesting thought. I have a question. Would you know why the COCO's performance is very significantly lower than full CUDA? Because
yes,
we have tested this on another code, and we had quite similar performance, maybe 5–10% loss only with COCO's, and you seem to have a much greater loss of performance.
Yeah, sure. So that's mainly a couple of things. So one is parallel reduction kernels. So when we use CUDA, we use this this kube. I think that library comes from CUDA Unbound. It's this CUDA library which have parallel reduction algorithms, and with CUDA we use that. With COCO's we just use the COCO's default parallel reduction call. I don't know if it's possible to select different parallel reduction algorithms with COCO's, but there seemed to be a significant slowdown from parallel reductions from COCO's. And other thing is that with COCO's we are not able to use this CUDA memset operation. With CUDA we use CUDA memset to initialize arrays, and it's faster than the approach taken in COCO's, because with COCO's we either initialize these arrays using these COCO's view types or using a COCO's compute kernel, and those are significantly slower than using this CUDA memset call. And I think the third thing is that with COCO's, the way it's implemented right now, we are not able to use direct GPU-GPU communications through MPI, because we have completely architecture agnostic COCO's implementation, so that we don't have any COCO's calls where we use CUDA specific template arguments. So we are allocating these MPI transfer memory buffers using unified memory, and then doing this host staging operations where we copy the staging buffer from unified memory to host memory, and then pass pointer to that host memory buffer to the MPI library. And that is the way it's done with COCO's. But when we use CUDA, we just use pinned GPU buffers and pass those to the MPI library, so it can do direct GPU-GPU transfers. We could do similar thing with these direct GPU-GPU transfers with COCO's, but it would require COCO's function calls with CUDA specific template arguments, which wouldn't work, for example, with AMD cards. So now, because we have two backend options, CUDA and COCOS, we want our COCOS implementation to be fully architecture agnostic and work with all vendors, let's say AMD, NVIDIA, etc. So we don't want to use these CUDA specific calls, because for them we have CUDA backend option, if that makes sense. So basically the difference between the performances come from these three things. So parallel reductions, CUDA memset for array initializations, and MPI like direct GPU MPI transfers. So those three things contribute to almost all the overhead.
Okay, thank you.
Thank you very much, Jaro. I think we'll cut it here.
Yeah, thanks for your interest.